degradation in crystal materials, in particular, how the various environments could lead to significantly different modes of the microstructure evolutions. And then in the second story, I will introduce how to understand and identify the non-conventional defects in amorphous glossy materials, but from the perspective of potential energy landscape. In particular, how these defects are influenced by the surrounding environment and how do they correlate with materials properties. And in the end of each story, I've also spent some time discussing the broader implications. So here we start. As initially proposed by Goldstein and further developed by Stillinger et al., the materials evolution is actually governed by its underlying potential energy landscape. So here is a simplified illustration on PEL. So basically, it consists of some local minimum, known as the basin state, and some settle point, known as the transition state. And materials evolution actually corresponds to the hoppings or migrations between the different local minimum on the PEL. And the hopping rate, according to transition state theory, is determined by the temperature and the activation barrier. So the energy differences between the local minimum and the nearby saddle state. So according to such Arrhenius law, for the relatively low temperature or high barrier situation, now the hopping rate slows down very quickly in an exponential manner. So that's why under such circumstance, if we still employ the traditional, say, molecular dynamic simulation method, then the system will be trapped and keep rattling in the initial given basin forever, and it can go nowhere. So to solve this problem, let's think a little bit differently. So what if we know the structures of the PEL in our study? Say, if we know where the local minimum are and where the nearby saddle states, we can then directly input these parameters into the transition state theory, and thus would be able to probe the long-time scale behaviors without employing the traditional MD method anymore, right? So following such idea, we thus employed some atomistic technique that are able to probe the structures of the PEL in our research. So at first, in crystal material system, because there are very distinguishing defects and the corresponding PEL structure is relatively simple, and under such circumstance, we employed a very efficient algorithm named autonomous basin climbing method. So the basic idea of this ABC method is that by filling many small droplets of penalty function into the initial given basin, the system can be gradually lifted and then being pushed over a nearest saddle state and then relaxed to the next neighboring local minimum. So by keeping doing these procedures, we are therefore able to probe the local PEL structures. And on the other hand, for glossy materials, because of its disordered atomic nature, now the PEL structure becomes very complicated. And under such circumstance, we need to employ a more rigorous and a mathematical algorithm named activation relaxation technique. So the basic idea of this art method is that starting from the initial local minimum, then you introduce small perturbations along the randomly selected different directions. And this would generate some non-zero forces. And by analyzing the variation of the system's mathematical structure of the underlying Hershey matrix, we would be able to push the system evolve towards the uphill direction and thus identify where the nearby saddle states are. So both methods can provide us useful information on the PEL, and as mentioned before, these hereby obtained parameters would be then fed into the transition state theory to enable a long-time scale modeling scheme. So this is a basic idea. However, so far our discussion has been limited on a static picture, that the PEL itself is fixed and the activation barriers are at a constant value. In reality, however, in particular where we have very complex, time-dependent, and non-equilibrium environment, now the PEL itself will be changing accordingly. And activation barriers would become time-dependent as well. So now essentially we have two different time scales. So the first is an intrinsic time scale, so still the hopping rate at a given activation barrier. But the second time scale would be an extrinsic time scale, means how fast the PEL will be changing under the surrounding environment. And you could imagine that naturally there will be a coupling effect between these two time scales. And the mathematical details on this coupling effect can be found in our paper listed here. But in today's talk, in the interest of time, I will skip those details and only show you the derived results of the real transition time inside a basin, but under a time-dependent scenarios. So you can see that this coupling effect leads to a very complicated, highly nonlinear expression, and we need to keep this in mind, especially when dealing with a complex environment. So now, with the method preparation, let's get into the first story on the conventional defects-mediated degradation in crystal materials under the complex thermal-mechanical environment. In particular, I will show you how the same unit process of a defect interaction could lead to significantly different mechanisms over the time scale span more than 10 orders of magnitude, from the ordinary experimental condition to extreme strain rate. Well, let's see some background first. We know that the mechanical properties of the crystalline system are largely controlled by the interaction between dislocation and obstacles inside. And in FCC material, one of the most common obstacles is the stacking fault tetrahedra, the SFT. So here is an in situ TEM experiment on a gold thin film. So basically, by applying strain to the sample, the dislocation can move towards the SFT. And people observe that this obstacle is eventually, you can see that, absorbed by the dislocation, and it will move together with it in the end in a jog structure, as shown by this image here. However, in a parallel MD simulation, people found that the moving dislocation, they just simply pass through this SFT, leaving the obstacle structure unchanged in the end. And similarly, in HCP material, experiment shows clear formation of dislocation channels, indicating the absorptions of the obstacles by the moving dislocations in those slip planes. However, in the independent MD simulation, people find again the dislocation simply passed through the obstacles, leaving its structure unchanged in the end. So resampling the features in FCC materials. So now the question is why people got this different and controversial result. So if you look at the conditions where these different studies have been made, you'll find a major difference is that in real experiment, usually the applied strain rate is pretty low, smaller than 10 to the minus 2 or 10 to the minus 4 per second. However, in the MD simulation, due to its intrinsic timescale limitations, the applied strain rate has to be very high, larger than 10 to the 6 per second. So could this huge gap, almost more than 10 orders of magnitude in timescale, be the underlying reason for such discrepancies? And because now with our novel PEL-based modeling, we are able to probe the atomic details at much longer timescales, and therefore I would like to employ such method to examine the interaction mechanism between dislocation and obstacles to see why and how exactly the different mechanisms could happen. So here we consider an HCP zirconium because it is a very important material widely used in the advanced nuclear energy system as a cladding. So basically, the neutron produced by the fission reaction inside the fuel will create radiation damage in the outside cladding materials. Any interaction between this location and this irradiated defect will determine the degradation or even the lifetime of the system. So to better elucidate the previous controversy, here we examine a unit process of defect interaction between a moving dislocation in the prism plane and a SIA cluster inside the basal plane. So the geometry illustrations and the detailed atomic configurations of these two objects are shown here. So basically, we would like to investigate their interaction mechanisms over a much wider range of thermomechanical environments far beyond the accessibility of the traditional atomistic method. So we first consider their interaction under athermal conditions. So at first in our simulation, we quench out all the thermal activation and only induce a pure shear into the system. So here are the strain stress curve and a few critical configurations along with this interaction. So starting from configuration 1, we apply a shear and push the dislocation move towards the SI cluster. So you can see that the two objects, they start to contact with each other and ping to each other and eventually detach from each other. And very interestingly, if you look at this final configuration here, you'll find both the dislocation and the SIA cluster structures got fully recovered to the original structure before the interaction. So basically, the dislocation simply passed through the obstacles and nothing happened in the end. And this, in fact, very well consistent with earlier others' MD simulation result, if you recall. But now, let's turn on the temperature and consider different applied strain rate. So here I show you the strain stress curves at room temperature, but with applied strain rate of 10 to the 5th per second down to 10 to the 3rd per second, already far beyond the accessibility of the MD simulation method. So at first, we found that the critical stresses at finite temperature is always smaller than its value under athermal condition, which is as expected because thermal activation would actually facilitate the atomic ray arrangement and therefore could make this yielding happen earlier. But very interestingly, if you look at the final configurations at this different environment, you will find at the higher strain rate of 10 to the 5th per second, the dislocation again passed through the defects. So following the same defect recovery mechanism. as in athermal conditions. However, for the lower strain rate of 10 to the third and 10 to the fourth per second, we find that the SI cluster is eventually absorbed by the dislocation, and it will move together with it in the end in a jog structure, as shown by configuration A and B here. So here comes the question. Why? The same unit process of defect interaction could lead to significantly different mechanisms. So if you carefully examine the structures of a strain stress curve on the left-hand side, you would find at these conditions, there are two interesting bump structures on the curve which are missing at higher strain rate conditions, indicating that this defect removal mechanism might be related with these bumps. And because in our modeling, all the atomic details are retained, therefore we can easily trace back to this point to see what exactly happened here. And by doing so, we found indeed such bump correspond to a trigger event. And in this slide, I show you the corresponding atomic processes in that trigger event seen from different angles. So basically, in this reaction, the few atoms near the dislocation core, so these atoms here, they are pushed upwards. So you can see this reaction pretty clearly, right? And such reaction actually induces a relatively low density structure near the original core areas. So from this angle, you can see clearly you have sort of hollow structures in the original core area because you have more atoms are pushed upwards. And such structure thus further facilitate the dislocation climb over and eventually absorb the SI clusters. So therefore, this trigger event can very well explain this defect removal mechanism. However, another natural following question is why? Such trigger events only happened at lower strain rate conditions. Why doesn't it occur at high strain rate environments as well? Since we know that whether an event could be activated or not depends on whether there is enough time for the corresponding atomic rearrangement process to take place, which is then determined by the associated activation barriers, right? And therefore, in this slide, I show you the activation barrier profile for that trigger event under different shear strains. So we find a very interesting non-monotonic behavior with a non-zero minimum, as shown by this purple triangle here. And this is very important, because we know that there are in total two driving forces in this interaction, the thermal activation and the applied strain rate. So for thermal activation, the higher the barrier you have, the longer time it requires for this event to be successfully activated. Therefore, the corresponding time window for the thermal activation should follow the similar trend as in its activation barrier profiles. However, for the applied strain rate, the higher strain rate you applied into the system, the shorter time you could stay near the vicinity of a certain strain. So if the applied strain rate is pretty low, which means the time window is wide enough, you can easily match with the thermal activations. In other words, there is enough time for this trigger event to be successfully activated, which would then lead to a defect removal mechanism. However, if the applied strain rate is very high, then the time window is too narrow to match with the thermal activation. In other words, given such short time period, this trigger event cannot be effectively activated. Therefore, dislocation will just simply pass through the obstacles, leading to a defect recovery mechanism. And in fact, these different mechanisms can be better seen from the perspective of potential energy landscape. So basically, starting from the same initial state, we have two different evolution pathways for this particular interaction, which are the defect removal pathway and the defect recovery pathway, respectively. And at the very beginning, the path 1 has a lower activation barriers. Therefore, if the surrounding environment doesn't change or change very slowly, then the system would have a much higher probability to take path 1. However, if now the surrounding environment is changing very quickly, for example, under the extremely high strain rate, now we are pushing the system too fast towards the path 2 direction, and the corresponding activation barriers is significantly reduced for path 2. So that's why under extremely high strain rate, we've got a different interaction mechanism. But of course, here are still some schematic illustrations, right? In reality, we have to consider the analytic nonlinear coupling effect between these two time scales, as we mentioned before. So basically, according to our derived formula we mentioned before, we're able to identify the critical conditions or boundaries differentiating these two different mechanisms. And by doing so, we're able to predict a mechanism map for this particular interaction. So basically, we can predict that at the lower temperature and higher applied strain rate, the defect recovery mechanism is dominant, while at higher temperature and lower strain rate, the defect removal mechanism prevails. And now with this predicted mechanism map, we can then put the conditions of the previous controversial result from both experiment and simulation into the same map here. So here, this line represents the earliest others simulation condition, while this dot represents the experimental condition. So you could find that they actually align pretty well with our predicted mechanism map. So in fact, they do not contradict each other. Instead, they just represent the different reflections of the same unit process, but simply under the different environment. So now everything looks pretty nice, right? We're able to address a long-standing controversy here. However, I am not very satisfied. Because if you look at his previous studies, they sit either on this side or on the other side. However, to better validate such diagram, especially the existence and accuracy of our predicted boundaries, we need other very well-designed verifications that can go through from one side directly across the boundary to the other side, right? So this is what we did. We collaborated with a very well-known MD expert, Dr. Yuri, and want to do MD verifications. Yes, I mentioned several times before that MD has its own limitation and can only handle the high strain rate conditions. But in terms of this verification, we can do it smartly. We can go across the boundary from these directions by changing the temperatures in MD simulation. So we employed a very extensive set of independent MD simulations, and indeed, we found two different interaction mechanisms. So here, the open square represents the defect recovery mechanism, while the filled square represents the defect removal mechanism. So you can find that the independent MD test, they fit pretty well with our predicted boundaries here. So now we feel more confident about the correctness of this diagram because it can very well explain all these different independent verifications. And because these two mechanisms, they have entirely different mechanical consequences, and therefore this result here could be used to shine light on the thermal mechanical processes and therefore to manipulate materials behavior by tuning the surrounding environment. And also, such diagram here could also be used to provide more accurate mechanisms or better interfaces to the higher level models such as dislocation dynamics or finite element method, and can together build up a multi-scale material modeling framework. So in the next few minutes, I'd like to give you a brief outlook on the implications of this research. So at first, I believe this example would have some direct impact in many important applications listed on the right-hand side. Because the key is the material's performance is actually influenced by its underlying potential energy landscape. And the PEL itself is affected by the surrounding environment. And in this example, we only considered the mechanical loading effect, but it would be quite direct and simple to extend to other environmental variables as well, including the chemical reactivity, the pressure, the irradiation, and etc. So by applying the same method or framework, we would be able to get a better understanding of materials' behaviors on a more extreme environment, and thus would be able to optimize the performances and push the stability limit in these important applications. And in addition, I believe the similar concept employed in this example might be used to predict some novel metastable materials that usually cannot form under the conventional equilibrium conditions. So to be more specific, in this example, we demonstrated that by tuning the non-equilibrium environmental variables, it is possible to engineer the PEL structures, which then allows us to control the system's kinetics and therefore get a different final product. And in fact, the similar phenomena has been observed in many important energy applications. For example, people found that the different microstructures of the battery electrode can be formed by changing the electric field and the temperatures in the non-equilibrium hydrothermal processing. And therefore, our example here might help better predict or quantify the boundary between the different microstructures of the battery electrode, and therefore might shed light on the predictive design of the novel energy devices. So for brief summary, I have shown you in the first story that the conventional defects-mediated degradation in crystals under complex environment can be very well described by the potential energy landscape-based modeling. And now let's move on to the second story to see how to understand and identify the non-conventional defects in amorphous glossy materials, but also from the perspective potential energy landscape. Well, again, let's see some background first. We know that normally, when a high-temperature liquid gradually cools down, there will be a first-order phase transition. and the system would become crystals at low temperature, and the performance of crystals on external stimuli are actually controlled by their inside defects, as we just mentioned before. However, if now the cooling rate from the liquid becomes very high, then the material will be quenched into the non-equilibrium glassy state. And because of this disordered atomic nature, there are no longer these well-defined topological defects as in its crystalline counterpart, which makes the study of glossy material particularly challenging. And what's more interesting is that by preparing the glasses at different processing histories, for example, with different cooling rates, as shown by curve A and B here, then you would find the structure differences are very small. However, such tiny structure changes could lead to significant differences in the macroscopic properties. Well, let's see some background, real background. This is a recent experimental work on a copper zirconium-based metallic glasses. So basically, people prepared several samples with different thermal histories from the fast quenched as-cast condition to the better annealed condition. So here the solid curves are the structure factor, the S of Q of the samples measured by the X-ray diffraction techniques. Well, the dashed curves below are the differences between these samples, but magnified by a factor of 5. So you can see that the structure differences here are negligibly small. However, in a following mechanical test experiment on these samples, people found significantly different behaviors. In particular, for the better annealed sample, the system is extremely brittle. It can only deform a little bit and then will just break away. But for the fast quenched as-cast sample, there is a significant amount of plastic deformation, suggesting a much better ductility. And to explain such remarkable differences, the authors in this paper, they have to propose an empirical model where there have to be, at first, some universal defects in the metallic glasses. And secondly, the defect density has to be much higher in a fast quenched sample than in a better annealed sample in order to carry these plastic deformations. Well, such empirical model can partially explain the experimental observations, yet on the other hand, it also brought up some new challenging questions from the very fundamental level. For example, what exactly is an individual defect in disordered glossy materials? How could we understand that? And secondly, why the different thermal environment could induce different defect densities? And finally, how the different density could further lead to the different mechanical consequences. So these are the questions I would like to tackle in the remaining part of this presentation. But at first, according to this scattering experiment result, we know that the conventional topological analysis won't help much in identifying the defects in disordered glossy materials. So we have to take a different perspective. So what can I do? Again, bearing in mind the material's evolution is actually governed by its underlying potential energy landscape, I therefore would like to probe the features on the PEL during these elementary processes. And we mentioned before, the elementary process should correspond to the hoppings between the neighboring local minimum on the PEL, and such process actually consists of 2 stages. So the system needs to first activate from initial local minimum to a nearby saddle state, and then because the saddle state is unstable, the system needs to later on relax from the saddle state to the next neighboring local minimum, the final state. So we can call them the activation stage and relaxation stage respectively. And I would like to analyze the correlations between the different variables, including the activation barriers, the atomic displacement, and the atomic level stress changes in both stages to see whether we can find some universal patterns out of that. But please be reminded that the PEL structure is very complicated, particularly in glossy materials. It's in very high dimensions, and each local minimum is actually connected with tons of different nearby saddle states, and therefore we have to do enough samplings to get enough statistics. And to better compare with the experiment, here we also consider a copper zirconium metallic glass modeling system, and in our simulation we consider 2 different thermal environments. So system 1 was prepared by an instant quench from the high temperature liquid, therefore presenting a fast quenched as-cast condition. Well, system 2 was prepared at a finite cooling rate, therefore presenting a better annealed sample. And we would like to compare the deformation mechanisms in both systems. Well, now let's see some results. So here I first show you the activation energy spectra. Well, in other words, a statistics with respect to the activation barriers identified in both systems. So you could see that for the fast quenched unstable system 1, there is a very high fraction of the low activation energy event. Well, for the better annealed system 2, the low energy activations have been significantly suppressed yielding to a real peak at a finite value. So basically, the two systems show very different overall activation energy spectrum. Well, but this result is not that surprising. It is quite intuitive because you could imagine that for the unstable system should be more susceptible to small perturbations. However, very interestingly, if you check the relationship between the activation barrier and the maximum atomic displacement from the initial local minimum to the nearby identified saddle state, you would find the data point here align very well with a clear parabola curve. And a log-log analysis of this curve shown here provides us an exponent around 2, suggesting these elementary activation processes are essentially elastic-like behavior. And more importantly, although the overall activation energy spectra in the two systems are so different from each other, yet in this plot, the two sets of data points, they collapse very well with each other, suggesting the elementary activation mechanism is in fact system independent. So basically, here are some statistical results, and each data point in this plot represents a distinct activation event of the whole system. But now let's take a more detailed analysis to see how each atom would behave during this different activation events. So basically, here I pick up 2 randomly selected points out of these thousands of identified different events. And now let's see the relationship between the atomic displacement and the atomic level stress changes in those 2 picked up events. So now in this plot, each data point represents the response of a single atom. So you can see that for the vast majority of atoms, there are only negligible displacement or stress changes, yielding a linear background pattern as shown by this blue line. Yet, on the other hand, there are a few atoms on the right-hand side. They show significant deviations from these background fluctuations. And if you visualize these important atoms, you'll find that they are actually clustering in space, suggesting these elementary activations are actually highly localized processes. And now to accurately estimate the size of this individual activation event, we need to remove the less important background fluctuations and only count the number of those important atoms outside this blue shadow regime. So the mathematical criteria on how to select a self-consistent cutoff radius can be found in the method section in this paper. But in today's talk, I will skip those details and I will only show you the final results of the size distributions of this individual activation event in both systems, as shown here. So the first observation is that these elementary activations are really small, really localized. Look at the peak position. Only around 5 atoms are involved in the rearrangement process from initial local minimum to a nearby saddle state. However, more importantly, you could find the overall size distribution profiles in the two systems are almost identical to each other, which again suggests these elementary activation mechanisms in fact system independent. And this in fact is very well consistent with our earlier analysis based on the activation energy and atomic displacement data. But now you probably get a little bit confused because on the one hand, we already knew from the very beginning that the two systems are so different in terms of their overall activation energy spectrum and their macroscopic properties. Yet, on the other hand, I have shown you through different analysis that the individual activation mechanisms in the two systems are the same. So how to reconcile these two pictures? Where on earth the differences between the two systems come from? So here I show you again the relationship between the activation energy and maximum atomic displacement. So we saw this before. The two sets of data points, they collapse very well with each other. But now, if we make a statistics with respect to the x-axis, then we got a very interesting different behavior shown below. So basically, this picture tells us that for the fast quenched system 1, you're starting from initial local minimum, you just need to go a small distance. Then you would be able to find a nearby saddle state. However, for the better annealed system 2, you need to go further to find a nearby saddle state. And because this atomic displacement from the initial local minimum to a nearby saddle state sort of represents the separations between the neighboring local minimum on the PEL, and therefore this result here demonstrates the densities or distributions of the local minimum are remarkably different and they are thermal history dependent. So in particular, for a slowly cooled or better annealed, more stable system, the local minimum are well separated, very far from each other. Well, for the fast quenched unstable system, the local minimum are very close to each other. So although the bottom of each local minimum, they are identical to each other in terms of the same prefactor and exponent of 2, as demonstrated by this plot here, yet the different densities or different organization patterns, they naturally build up the very different overall activation energy spectrum, as we've seen from the very beginning. So this is how the two pictures reconcile with each other. And up to now, we're able to answer the first two questions we mentioned before. So at first, indeed, we can define some universal defects in disordered glossy materials. However, such defect better to be understood from the perspective of potential energy landscape. And secondly, the defect density is essentially related with the distributions of the local minimum on the PEL. So now let's take a further step, focusing on the later on relaxation stage to see what would be the consequences of these different defect densities or different PEL structures. So now in this plot, I show you the relationship between the energy relaxations and a corresponding maximum atomic displacement, but now from the saddle state to the final state. And each data point in this plot is colored according to the total number of involved atoms, but after these relaxation stages. So at first, we find a very familiar parabola curve indicating a localized relaxation mode. And such mode exists in both systems. However, very interestingly, in the fast quenched system 1, in addition to this localized mode, there is an extra branch deviating from these quadratic relationships. And furthermore, the events in this extra branch, they always include much more number of atoms than in these localized relaxations. And such features makes this extra branch essentially look like a cascade relaxation mode. And to verify this different picture, I made some further statistics with respect to the y-axis in this plot. So as shown by this result here, for the better annealed system 2, the overall distribution just follow a simple exponential decay. So this is also a mathematical feature of localized processes. But for the fast quenched system 1, the distribution shows a mixture of both exponential decay and a parallel decay at high energy end, with exponents around 1.6. And this is a typical mathematical feature of the avalanche or cascade phenomenon. And therefore, such analysis here very well support the picture we obtain in this plot. So now the question is why the two systems show very different behaviors in these relaxation stages. In fact, this can be very well explained by our previously obtained PEL structures, because we mentioned before in the better annealed system 2, the local minimum, they are well separated, very far from each other. And therefore, each relaxation would less likely to affect the surrounding eventual atoms. But for the fast quenched system 1, the density of the local minimum is so high and they're too close to each other. And therefore, each relaxation would have a higher chance to trigger an avalanche or cascade phenomenon. And because this cascade mode can provide us a more efficient energy relaxations in terms of its large magnitude in the y-axis, which means the externally loaded energy or strains could be more easily dissipated away. So that's why the fast quenched system should have a much better ductility than in the better annealed sample. So this can very well explain the last question we mentioned before. So now everything looks pretty nice, right? We're able to address a number of fundamental questions we mentioned before. However, I am, again, not very satisfied. Because after all, our predictions here are still based on the atomic level simulations. Yet the previous mechanical test experiments are at the macroscopic level. So there's still a huge gap between these two studies. So in China, we call this scratching the itches outside the boot. Basically means it's there, but not perfect yet, right? So can we find some more direct evidence, but also from the very fundamental level? And unfortunately, I found a very recent experimental work done in Europe at Grenoble. So these scientists, they employed an X-ray photon correlation spectroscopy, a very advanced technique that is able to probe the atomic details. So they investigated the dynamics in metallic glass, and by analyzing the patterns of the two-time correlation function, they observed almost exactly the same thing. So in their own words, these observations are consistent with our recent simulation, which shows that the microscopic relaxation dynamics is significantly more spatially localized in a slow liquid glass than in a fast quenched material. And they also mentioned that this observation reflects the presence of both localized and cascade relaxation dynamics, as predicted in our earlier simulation here. So you can see that they are very excited because they know now how to explain their experimental observations. And meanwhile, I am also very excited because such nice consistency here really demonstrate the potential energy landscape is indeed a powerful tool in describing the complex materials under the complex environment. So to summarize the second story, so basically I show you that indeed we can define a universal defects in disordered glassy materials. However, the defect is difficult to understand from the conventional topological point of view. Instead, it's to be better understood from the perspective of potential energy landscape. And the surrounding environment, they could not change the properties of individual defects, but they could change the densities or organization patterns between the different defects, which then determines the macroscopic properties of an entire system. So in the last minute or two, I would also to give a brief outlook on the implications of this research. So at first, because of its promising mechanical features like high strength, high resistance to wear, to corrosion, to irradiations, and etc., the metallic glasses actually have already been used in many important manufacturing applications. In fact, well, you maybe all have iPhone. This logo in this iPhone 6 is made of metallic glass. And Apple company has promised that soon the entire cases will be made of metallic glass as well. So certainly this research here can help optimize the performances of the metallic glasses in these manufacturing applications. But in today's talk, I would like to discuss its broader implications on something else, some other issues, like energy storage. For example, this is a summary made by International Energy Agency a few years ago on the large-scale energy storage in the decarbonized power grid. So among these different techniques, I can see at least two aspects where this research could show impact on. For example, it might help us understand the so-called mixed glass former effect in the lithium battery, which is a pronounced ion conductivity increase phenomenon related with the atomic rearrangement or diffusions in amorphous structures. And also, this research can certainly help us better understand the mechanics of glass fibers, which are widely used in the high-power flywheels. So to summarize the entire talk, basically I have demonstrated that the seemingly very different crystalline system and amorphous system can be well described by a unified framework based on the potential energy landscape. And this is very important because it really broadens our horizons and shows a bigger picture. Because now, under the same framework, we would be able to investigate the more complex material systems. For example, in the composite materials made of both glasses and crystals, they have a lot of applications. And also in the interfaces problem, particularly with green boundary systems, you could imagine that green boundary structures, they actually sit right between the perfect crystals and pure amorphous materials. And their performances under extreme environment in the future study can certainly help address a number of basic research needs outlined by the Department of Energy. But of course, this can only be achieved through the synergistic cooperation between experiment, theory, and modeling, as what I'm trying to show through this talk. And with that, I would like to thank you for your attention.
We have time for some questions.
You showed us that you have remarkable correlation between your model and experiments,
Right.
giving sort of the scientific proof that this works. And you've also outlined way out there how this could have implications for energy. I'm wondering if you can take us a smaller step from the implications of your work to what you might do to make a practical improvement in metallic glasses.
In metallic glasses? Yes. Well, certainly in future, I would also be interested in something else. But in terms of metallic glasses, indeed here, I'm sorry. Yeah, indeed here, such consistency, right? Demonstrate our model is sort of have some certain merit. But so far, this correlation or consistency is still at a qualitative level. So now I'm trying to further quantify such correlations. For example, how can we quantify this different number of local minimum densities as different processing histories? I hope I can get a quantified equation or formula, and that can guide the experiment. For example, how you make the processing histories to produce the required or demanded properties. This is one thought currently in my mind.
So is there an example of a property that you'd want to improve? Or
Sure, yes.
variables you'd be
Yes. The metallic glasses, they have, as I said, has most promising features like high strength, high resistance to wear, to corrosion, to radiation. But there is a drawback that is sort of brittle compared with the crystal materials. So how to increase the ductility of the metallic glasses is certainly a big issue in this material energy related applications. So in this example, I sort of demonstrate that if you could somehow you have higher density of local minimum, you sort of can make this, create some dissipation pathways, can make the material more ductile, right? So certainly this is, I want to keep going on this direction to help design or optimize the ductility of metallic glasses.
Can I just follow up on
Sure.
that? The actual deformation mechanism by which metallic glasses undergo deformation is usually by some shear band
Right.
process, right? I don't see that sort of popping out exactly
Sure.
from what you're showing here.
Yes, shear band is no longer a fundamental mechanism anymore. So here we are focused on very fundamental level, so it's sort of like a beta relaxation. So a very localized, or in Eugene language, it's shear transformation zone. It's very localized, small defect. But shear band is sort of propagation or highly collective, a number of STZs. They somehow connected together and propagate entire materials. So in that case, you need a larger system to see the correlation between the elementary process I'm studying here. So not right now, I'm still at a quite more fundamental level, but certainly that will.
So like in many mechanical properties things, you've got to go from this very atomistic level to the next level
Right.
to really understand what's
Right.
going on.
Yes, exactly. Because, for example, shear band, I'm going to say is, for example, if there's more, because shear band makes a material failure, right? So I want to see whether this shear band, how far to fundamental elementary, how far that they could be introduce a dissipation pathway, or they will be, percolated, induce a shear band. That's in my plan, but it would be a larger system. Yeah.
Yeah, I had a related question. Could you go back to the zirconium copper system you had up there?
Sure. Let me get. This one?
I was thinking of it where you had shown us 3 different or 4 different stress strain curves.
Right.
Quenched glass, and then for the annealed glass,
This one?
No, farther along in your talk, nor towards the end. You showed us that upon quenching this form of glass, it exhibited, I wouldn't call it much ductility, but it was pretty elastic, and there was a little inelasticity towards the end, perhaps a percentage so inelasticity or elastic strain. And then the annealed at 300, no strength and no inelastic behavior. And then as you went up in temperatures of annealing, you got a little more strength and maybe a little more inelastic behavior, right?
Let me put it.
That set of curves.
Right.
It's kind of following what you just showed us here.
This one, right?
Yeah, a little farther along, still further along.
You're talking about this one?
Yeah, that's right.
Yeah.
So looking at those, I'm saying, as you loaded it and cast it quickly, you got some evidence of inelasticity. The curve bent over, and the material was strong. Green curve.
Right.
Now I look at red curve, no strength, no inelasticity.
Right.
In both of those cases, those extreme cases, is failure occurring in the manner that Professor Baker mentioned, that is the development of a shear band?
Right.
Both cases. Okay, got it.
No. I mean, for this green case, I'm not sure about details. But for this red cases, that's certainly a shear band propagation.
So the students know that the reason metallic glasses are often very used practically, as though they're very strong, they're oxidation resistant, wonderful against corrosion. They just have no inelasticity. They're just plain brittle.
Right.
That's why they're not being used in that
Right.
sense.
Yeah.
So you've got to be able to solve that problem
Right.
before you can use their good qualities.
Right. Exactly.
What I'm trying to get at is the origin of that localization and how you can sort of delocalize your localization, if you wish.
Yeah. Exactly. So as I mentioned, for example, in this picture here.
Are we any closer there with this understanding?
Yes. I'm sorry. Maybe we can start from here. So basically, what we found that for a better annealed system, right, and it seems the local minimum, they are well separated, very far from each other. Therefore, the injected some energy or strain, they more easily get localized because they not easy to interact with the surrounding defects or atoms. So you get localized, and then it's just a burst, and then the material just fail. But here, if somehow you can create a lot of local minimum, fine structures on the PEL, then you sort of create a lot of dissipation pathways, right? The energy, that certainly can help increase the ductility, right?
So does the deformation band get initiated at this whole potential energy landscape?
Right.
Does it get initiated at that point in the landscape that has the lowest activation energy?
Has lowest what energy?
You've got a full spectrum of activation energies.
Right. I see. You got the activation energy spectrum. Right.
Start there, and then because of, I don't know, you got heating or something, stay there.
Yeah, that's a very good comment. I haven't checked the details because at first in our modeling, it's still pretty small system. We don't really see this shear band formation yet. So I cannot see the direct connection to the... Yeah, but certainly because if in the next plan I would plan to build up a larger system, hope can get some, because now it is possible in simulation to create some shear band. I certainly want to see the correlation between this initiation of that shear band with the activation barrier spectrum. Right. Yeah, very good comment. Thank you.
So you show us cooling rate as one variable that
right.
can, fast cooling can give you this structure that is better. Are there other things that you would study, composition, or what else would you be studying next, and do you think that might give you better material?
Exactly. Certainly, if you want to engineer the properties of the material, you want more degree of freedom to control them. So now, in fact, there have been very recent experiments shows that in this steel metallic glasses, after the irradiation, for example, proton irradiation, then you compare the unirradiated sample and irradiated sample. You do the mechanical test, you would find the irradiated sample have much better ductility than the unirradiated one. But in terms of the X-ray scattering, you do the two samples, again, almost identical to each other. But this experimental study, that have not been published yet. I saw that in a conference in January. I have a lot of discussion with him. I want to certainly investigate the irradiation effect, for example, in metallic glasses, to see whether that will introduce some differences in the energy landscape. Exactly, and because I had some experience on irradiation in my PhD work, I certainly want to apply that. And another issue is in terms of this composition chemical effect. Last year, or maybe 2 years ago, there was a modeling. Then trying to tune this bonding strengths between the atom pair. Right? That in simulation is easy to do. They find you just change a small bonding strength between atom pair, it could lead to significant differences in the mechanical behaviors in terms of the embrittlement or ductility. So certainly I also want to check how you tune this bonding strength could lead to the differences, whether there is any correlation between the PEL structures. And this certainly will give us more flexibilities in controlling their properties. Yeah.
I'm working in this field, but just out of curiosity, because you show a lot of minimum totally spaced in the lower figure, which gives you much different properties in terms of mechanical response. So I was wondering, there's another way to say, you can say this is basically a higher entropy, right?
Yeah.
So is that correlated somehow to the mechanism of how the high entropy alloys really works?
Yeah, that's a good way. Yeah, I believe so, because the fundamental idea why high entropy alloy works, especially why they have a very high resistance to irradiation, because now a lot of the application in the proposed use in nuclear structure material. That is because after the irradiation, you have some defect. You have so many, say, equivalent side, right? You can get more easily recovered to some lattice structures. So that gives you ultrastability. So indeed, I do see close connections here. And in particular, in high entropy alloy, although it looks like you have some lattice structure, but in reality, if you make a more detailed analysis, you would find there are also a significant amount of local distortions or local stress changes, also very different from the traditional crystals. And in fact, in that perspective, it's more similar to metallic glasses. And in fact, a lot of people in high entropy alloy community, they are from the metallic glass community. There's very strong connection there.
Could you tell us a little more about
Right. So this model so far is pretty small. It's 2,000 atoms. So basically, at a high temperature, we first at a high temperature heat up to high temperature 2,000 Kelvin, and it becomes this essentially a metallic liquid, right? And then we do this cooling. And then one thing is the system one was just make an initial instant minimization. That's an instant quenched condition. But the system two was we prepare cooling at a finite rate. It's still pretty high because to avoid this crystallization, but still a finite cooling rate. Then in the end, you got different samples with different energies. Although the G of R looks pretty similar, but they have very different properties.
Well, were you able to notice any differences in the interatomic correlations, neighborhood correlations? Is there any local structure variation between different conditions of cooling?
Right, but these correlations can be defined in many ways, which kind of very coarse-grained correlation, like peer distribution correlation, G of R. In terms of G of R, they look almost exactly the same. But if you consider some chemistries, some other group, for example, Professor Evan Ma from Johns Hopkins, their group, they try to develop some local extrahedral, polyhedral, that kind of structures. For example, copper-centered extrahedra. They believe that is sort of more stable site. So if you prepare the sample at a lower cooling rate, you have more concentration of the copper-centered extrahedra. That could also make sense. But I mean, we have also discussion with them. We found that they have some propensity, but the correlation, the fluctuation is so huge, so it's difficult to get a quantitative relationship. Certainly there is some correlation, but difficult to develop into theory in the future.
So if you take different batches,
right,
nominally the same but statistically different, and do the same simulation on them, how close do you get to the same result?
Same result in
we've got a particular fall off.
Wait a second again. I didn't follow you quite well.
Well, if you redid the experiment,
a simulation. Yeah.
Simulation with a different statistical
right
bunch of atoms, how close would you get to the same
result
failure?
here? Yes. In fact, we got this is pretty repeatable. Now, this is very sensitive to the size of the simulation box. We found if you go beyond several hundreds of atoms, now we have 2,000 atoms. So if you say do instant quench, we did this. Did say 5 or 10 different instant quench. And after that, we got this activation barrier spectrum, or the similar thing we've done before, as shown here. They're pretty well consistent. So the discrepancy is very, very negligibly small.
And you get the same result if you were to increase the size? You get the same result for 1,000 you got for 2,000?
Well, I mean, for this particular potential energy landscape structure analysis, we only have 2,000 atom system size. But for smaller size, we computed the energy. We didn't do the detailed PEL structure, but we compared the inherent structure energy. That certainly you have a size effect, but beyond 500, you already average energy per atom. They already get very well a narrow band. This one, right? Yes. Mixed glass former effect. So basically, in lithium battery, I'm not an expert in this area, right? But I read some literature. It seems that in lithium battery, you could have this either crystalline structure, but you also have a bunch of glossy structures of lithium battery, like with some. Let me show you. Let me show you another presentation. But I mean, maybe I can take other questions first, and after that I can show you a picture. Because usually in some other visit, I show a separate research plan. In that, I have some summary, some review paper by other peoples. So I can show you that figure. Probably you can catch up more from that.
I have a final question
Yeah.
here for you. So the metallic glass you were showing only had two components, right? Zirconium and copper.
In our simulation, right. But in real experiment, the dominant, there's a little bit more, sometimes 3, or 4. But the dominant composition are copper zirconium.
Right.
Yeah.
But my question is, we were talking about high entropy alloys. So
Right.
high entropy alloys have at
4,
least
5,
Well,
yeah.
they have, by definition, they have 5,
Yeah.
right?
Yeah.
Elements in there. So can you actually
Simulate
do
that?
simulations on high entropy alloys or not?
I don't see a fundamental or formidable barrier for that. Of course, you have more calculation.
Well, there's no theoretical barrier, but is there a practical?
Yes, but I mean, it's doable. At least, for example, 3 element, it is doable. And 4 element, from my opinion, it's just a complexity of this computation. You still use the Newton equation, you still use the same framework, but when the initial potential preparation, because you have more elements, you have more interatomic interactions. That is.
But when you get to 5, is the time taken to do the calculation?
I think that is separate from the doing simulation. But the initial preparation, you take a lot of time. But when you set up, that would be good. Yeah, but I mean, in terms of the fix this potential for 4 or 5 element, making the potential fitting is a huge amount of work, which I don't care about that. I rely on the potential they provided. But I guess that is a very challenging work. Yeah.
So we have time for one last question.
So in the first story, you talk about the change of mechanism,
Right.
degradation, current degradation, and you use experiment
Right.
to verify your
Right.
prediction.
Yeah.
And you only show the result at high strain rate. How about experiment at low strain rate?
No. I'm showing you the experiment in low strain rate because experiment is difficult to go to high strain rate. Yes. So. Okay. So you see, here experimental condition is very low, lower than 10 to the minus 2 or 10 to the minus 4 per second. Okay, but in MD simulation, it's much higher. What do you mean? Right, yes. Right. Low strain rate, how low? I mean, here is already reached to, this is MD verification, okay? This entire diagram is by our PEL-based modeling. We are able to access the entire regime. But I mean, this is just verification. But MD, we want to verify differently. But in terms of MD verification, they can only handle these high strain rate conditions. But we are able to access here.
So I mean, is it possible that experiment
Uh-huh.
and the boundary condition to show that you are creating this crack?
Yeah, now I have a lot of discussion with experimentalist because maybe experiment, usually the strain rate you cannot extend too much, right? But we want to discuss whether you can low down your temperature, go across from this direction. Yeah, I have a discussion with some scientists. They said it's difficult to reach to this low temperature. But I don't know, you do experiment? Do you think it is possible? I would love to have more collaborations here.